Great. So I think that I'm sharing this little notebook here. You guys hopefully see me doing things on the screen here. Yeah.
Yeah.
Yeah, we can see it.
Okay, good. All right. So some questions came up in office hours, and I realized that I think we didn't really talk about this issue of normalization very much. And so we're gonna go over that a little bit. And there are two of the three worksheets that we're gonna do today involve this step of normalization. And so remember that there's a rule that our probability density has to satisfy, that if I integrate over the entire domain, I get one, right? And for a density that has this property, we say it's normalized. Now, technically, anything that doesn't have this property is not a proper density. But there are a lot of situations where we have to create our probability density by binning data. For example, you create a histogram, and then you have to use the histogram as the approximation for the real probability density. And another case where we encounter this idea of normalization is when we find the probability density from some physical law. And in many cases, we find that the physical laws tell us the shape of the distribution, but they don't tell us the normalization. Okay, they don't tell us how tall it is, basically. And we have to set how tall it is, given the shape, by putting some constant out in front, so that the integral over that density comes out to be 1. Okay, so this is basic. That's basically it. That's the nuts and bolts of normalization. But let's just do a very quick little thought experiment. Imagine that we were collecting data on some property X, and we created a histogram. I think probably most people are comfortable with this idea of creating a histogram. If you are not, let me recommend that you can go ahead and do something now to prepare yourself for a couple of weeks from now in the class. We will be doing a lot of data analysis stuff with ANOVA, regression, hypothesis testing, and there is a whole packet of tools in Microsoft Excel. So, usually if you take this class from almost anyone else, they will make you learn R, or they will make you learn SAS, or they'll make you learn Minitab, some special software that you only use for statistical analysis. And I find this to be a real nuisance, because the truth is, everything that those programs do is in this free add-on called the Microsoft Data Analysis Tool Pack. And if you download that and you install it, it becomes like an extra tab in your Excel. And whatever data you're working with, you have all the power of all those fancy statistical programs right there within Excel, and you don't have to do the porting of your data back and forth between the two platforms, which is always something I despise doing. Okay, so that's a little tip for you. So you can do in practice the thing. You could take a whole column of X values and create a histogram using that Microsoft Data Analysis Tool Pack. But for now, let's just imagine that we have these little windows. So the beginning of my window is X0, X1 is the edge of the next window, X2. Oh, windows and bins. I use them interchangeably. That comes from molecular simulation. We always refer to our bins as windows. A long story why that is. But we go out till we get to Xn, and that's the end of our data collection. Okay. So then what we do is we fill in these little bars. This is the making of our histogram here. And, it's sort of a discretized version of a probability distribution. Okay, so maybe it had some, I didn't draw the middle part of this, but maybe it had some peak in the middle and then went back down on the edges. And that now looks like a discretized version of a density, if you want. And in fact, we can compute probabilities to be between X1 and X3. We would say that this is the real thing. That's the real probability to be between X1 and X3. But all I have is this data that I collected. And so what I can do instead is to add up so if these are the heights of each of these bins, then I would add up the height at X1 plus the height at X2. And I'm keeping track of them. This bin has a height that's indexed to that point on the left. Okay, I could also index it to the point on the right. And then what I'm going to do is divide this by the sum over all of the bins, like this. Okay, Now, why do we have to divide by the sum over all the bins? So this represents a probability, and this is a count. This is a count of the number of times you landed in those two particular bins. But we know that we want to convert that into a probability by dividing by the total number of counts. Okay, so this is something that you sort of innately know, that you have to normalize these things to say something about a probability, right? So if you want a fraction, which is kind of in many ways analogous to a probability, you have to normalize these counts. All right. So that's one situation where your probability density idea comes up. By the way, if you want to write down something that actually approximates the density, then you would say that rho of x itself, I would have to write it as the height of the bin located at x. And for any x, I look in this recipe to the point to the left, and I look at the height of that bin. And then I have to divide by the sum over all of the bins, h at xi, and I have to take the width of that bin. And the way I've drawn it, all the bins have the same width, but that doesn't necessarily have to be the case. All right, so why is that delta xi important down here and wasn't important above? Well, I assumed when I did the formula above that all the bins have the same width. If the bins have different widths, then I would have had to do this. Okay, and now that becomes the proper normalization for this thing. Now, usually when we create a histogram, we make all the bins have the same width, and so you can get away then with saying that you just ignore these because they all cancel. Okay, but when you write down what the probability density is, you have to keep that bin width at the bottom, because what this integral is going to do, if I literally compute this integral and I replace the rho by this formula, then my integral becomes a sum over all the values of I from 0 up to n minus 1. I'm going to put in that thing for my integrand. So this is, sorry, decided to stop writing, h of xi over h. I have to be careful here. So I'm summing over I, but I've got a normalization that has a sum over I. I'll just change that to a sum over j. So this down here in the basement is now a sum over all of the j's of h of xj, delta xj. And then my integration now became a sum, and I have to multiply it by all of the xi's. And you see that the numerator and the denominator are the same thing. Okay, this is just a number sitting down here in the bottom. All the j's have vanished. And this is the same number draped over the top. Okay, so hopefully that gives you some idea how we take data and build probability densities, and how we construct histograms, and that normalization is a critical part of that, right? So in all of these formulas, you see this thing down here in the basement, and that is a normalization factor. It's counting up all the hits and dividing each one of the hits in every particular bin by the total number, so that you convert it to a fractional amount in that bin. And then we can begin to interpret them as probabilities. So this is, people will talk about this very, very highbrow language here, the frequentist perspective on probability. Okay, is where you start from data and you think of the probability distribution as actually just something that reflects the frequency of landing in certain ranges. Okay, so what is this other situation where we find rho of x from a physical law? So this is kind of a reprise of office hours yesterday. Thank you to those who came and inspired this little intro today. But what we're going to do now is remember back to our quantum mechanics class when we solved the Schrodinger equation, and we would solve equations that look like this. All right, and please don't ask me to write down the operator here. It's some constants multiplied by a Laplacian, and allow me to drop all those constants and like a real theorist here, um, and uh, and just remember that basically what I'm going to get are boundary conditions. For example, if I did this as a particle in a box, the particle is confined to a range 0 to L. Remember what we got for the eigenfunctions in this particular problem. The wave functions in this particular problem were functions of the form. So the ground state wave function is going to be something of the form sine of pi x over L. And there's a coefficient out front. And it doesn't tell me how big that is. No matter what coefficient I put in front, if I plug that in here for psi, the coefficient comes right through, and I still have a ground state wave function that's valid. But the ground state wave function is only normalized for one particular value of that coefficient out in front. So when we normalize, so when we start from physical laws, for example, and you can do this with all kinds of problems in statistical mechanics as well, you get a shape of a distribution, but it doesn't specify for you how tall it is, right? So we know it's shaped like a sine function. We know it's the sine function that goes to 0 at both ends of both edges of the box, and I have to decide what to multiply it by so that it has a proper interpretation as a probability density. So if a particle is sitting in this ground state wave function, I know that I can think of the probability. Let me write this down properly. So the probability to be at a location, the probability density to be at a location x is going to be equal to my psi squared. And for this case, that's going to be whatever I put out front multiplied by the sine squared of pi times x over L. All right, so let's redraw the picture. We now have squared this function, and we got something that looks like this. Okay, so this is now the sine squared function, and that can be integrated over any subregion to say what's the probability that it sits in that little interval. All right, and now what I want to do is to be able to require that if I integrate rho of x from 0 to L, I should get 1. Okay, what I actually get when I do this integral is I get the coefficient squared times L over 2. There are easy ways to derive that, but please take my word for it that the mean value of this function so it goes up to a maximum of 1 in the middle, starts at 0, and the mean value here is 1/2, and the interval length is L. Okay, and so that integral comes out to be L over 2, and I wanted it to be 1, right? So what we do is we say we normalize this distribution by choosing the value of the question mark coefficient in here, so that does give us 1. And so what we find is that this normalization factor has to be equal to the square root of 2 over L. Okay, so now we would say that the properly normalized eigenfunction is the one that has 2 over L times sine of pi x over L. Okay, and the whole purpose of this is only to ensure that this thing comes out to be 1, so that we can properly think of this as a distribution. So we say that this is now normalized. Okay, so we do normalization all the time to ensure this. Okay, so let's with those ideas in mind, let me give you guys just a minute or two to ask questions, and then we'll load up the Prairie Learn site. And please open the exercise that talks about, maybe Zichu can help me here. Please open the exercise with the quote from Garrison Keillor. All of the children in Lake Wobegon are above average. Okay.
Yeah, I think it's just the first one. It's called Everyone Above Average.
Okay, everyone above average. Okay, that's the one that you want to open in the Prairie Learn site, and we will work that problem. All right, so I find this very amusing because it completely defies your intuition that this surely is nonsense, and I'm sure that's why he said it, because it seems funny. And yet there are distributions for which statements like this are true. And so we somebody wrote at one point, I love checking my common sense at the door in this class, and this is what we're going to do today. Okay, so we're going to see an example of a distribution that's perfectly well defined, and yet it ends up giving you these sort of nonsense statements like all children are above average. Okay, you guys have any questions about the idea of normalization? If not, then we will go ahead and start this problem. Okay, so we have a power law distribution. And a power law distribution, you find lots of examples of these things. For example, if you look at wealth in the United States, it's a power law with a very long tail. All right, so this is the distribution. Let me sketch a little picture of this so we all know what we're talking about before we get too far into this. So here's the point. Oh, sorry. I wanted to start my distribution at 1, and it's 0 for everything to the left. Okay, so my density is 0 for all things to the left of 1, and then right at 1, it jumps up and begins to fall off. But this is not an exponential. This is a power law, and so the tail, in principle, can be much longer than an exponential, right? An exponential, we say, is a quickly decaying function, and a power law, depending on the power, can be very slow. Okay, so for example, if I let A be equal to 1, then this is going to have a very long tail and won't even be possible to normalize. Okay, guys, we're gonna see all these weird quirks of this power law distribution. If I let A be equal to 2, then I will be able to normalize that integral, no problem. But some other weird things will happen. Okay, so let's go ahead and do that. So this is our density out here. And the first question asks us to find the value of A. So we're going to find big A as a function of little a. And our goal in doing this, what tells us that, the only thing that tells us that A has a specific value, only one value, one unique recipe for finding A that would be correct, is that this distribution should be properly normalized. Okay, so we're going to do that so that rho of X is normalized. All right, so let's go ahead and dive in. What does the normalization requirement say? It says that the integral over the entire domain of rho of X should be equal to 1. And if I now simplify that integral, I know I can write it as an integral from 1 up to infinity of a x to the minus a dx. Okay, and now that just using your standard integration tables, if you want, hopefully you guys remember this one, is going to be ax to the minus a plus 1 over 1 minus a. All right, so this was, I messed that up. Sorry everyone. So this would be.
Baron?
Yeah.
Can you maybe rotate the iPad? Students are saying it's a little hard to
Thank
see.
you. Thank you for alerting me to the issue there. All right. All right, so that confused it, and I have to close it and reopen. All right, I think that should be better now. All right, so this should be x to the power 1 minus a. Okay, so we just used the power rule for integration. So we took our exponent, we increased it by 1, divided by the exponent. And we have to evaluate this at infinity and at 1, okay? So if I complete my integration here, I get a over a minus 1, and that ends up, remember that I have to require that should be equal to 1, okay? Okay, so I want to make this thing equal to 1, and so I have to choose my constant a to be little a minus 1. Okay, remember the logic here. Big A is just a constant prefactor. It does not affect the shape of the distribution. It only affects how tall it is. Okay, little a, I'm not allowed to change. That's something prescribed that tells me about the shape of the distribution. So little a we think of as a parameter, and big A we think of as a normalization constant. Okay, and that normalization constant, as you can see, depends on the parameter. Okay, so just to help with some of the terminology here, that's what we have just done. All right, so I believe that that's the first question in your Prairie Learn exercise. Everybody can go and enter that, and then I will start on the next one here in about 1 minute.
Also, can you make it maybe full screen, the window?
It's not full screen.
No, you shared the whole desktop, so it's kind of small.
Oh, okay. Sorry. All right. Thank you. I've got my little faces of everybody in the way. All right. All right. Okay, good. All right, so now what we're going to do, so we should, before we go on, really think carefully about this result that we just did. You know, we kind of went recklessly and did these integrals. And of course, if you plugged these into Mathematica, it would know to tell you, be careful, do not let A equal what? Yeah, the chat is, I can't see the chat when I do the full screen. Okay, let me figure out how to get the chat in a separate box here somewhere. More chat. All right, I'm going to move the chat over to the other screen. Great. Okay, good, Nikki. So if we let A be equal to 1, we have a problem. Now, clearly, I also have a problem if I let A be something less than 1. So if I let A be 1/2, then this is going to diverge, right? So all numbers 1 or smaller are going to create a problem here. I cannot properly normalize the distribution. Okay, so I should be careful when I do this and remember that because of normalization, let me write this down. And this is required for it to be a true probability. We need A to be greater than or equal to 1. Okay, so that's the requirement imposed by the need to normalize our distribution. We've already learned that this parameter A had better be greater than or equal to 1. Otherwise, this integral that I did here will diverge. Okay. All right. So let's go on and do part B. So in part B, we're supposed to find the mean of this variable x in terms of A. All right. So we know how to do that. Let's say that mu is going to be equal to the expectation value of of x itself. And we can compute that by integrating from 1 up to infinity of x, rho of x, dx. All right. Let me put I should maybe, when I write it like this, I can go ahead and put the whole thing in. Now let me break this down and actually write what, all right. I think that's where we're going to start. Okay. So now we have, now we're integrating, we, by the way, know this value of A. Okay. Okay. So I could write that down as just some function of my little parameter A. Maybe I should do that. So we know from part A that this is x minus 1. We know that this is x to the minus a still, and this is my integral over dx. All right, so this is now an integral of x to the power 1 minus a. So that's going to end up being a minus 1 times x to the power 2 minus a, using the power law again for integration, over 2 minus a. And I have to evaluate this at 1 and infinity, okay? And so what happens when I let x go to infinity? Well, assuming that a is bigger than 2, then this thing in the numerator is going to vanish, okay? If I let x be smaller than 2, or sorry, if I let a be smaller than 2, then I have a divergent thing upstairs again, okay? So now we have another restriction. We find that a has to compute the mean, a has to be larger than 2, okay? So we'll go ahead and write down the result. So it's a minus 1 over a minus 2, and that's my expression for the mean. But to write this down, I had to require that a was greater than 2, okay? Oh, my goodness. You guys let me get away with this error. This is greater than 1, okay? Not greater than or equal to. Nikki told us that it can't be equal to 1 either, okay? So this is greater than 2 and greater than 1. All right. So now when we did our calculation of the mean, the average, we learned that a had to be greater than 2 for that average to exist. Now, what does it mean if I have a distribution with something like, let's say we put in 1.5 for the parameter a. So if we did a equal 1.5, I can normalize that distribution. I can calculate the number of the fraction of children that lie in any particular interval, and yet my mean diverged, went to infinity, okay? And that means that for this distribution with ax to the minus 1.5 power, all children would be below average. So it's kind of the opposite of the Garrison-Keillor statement, but it's a similar problem, right? That you do have distributions where the mean diverges, and yet you can properly compute probabilities to be in any particular interval, right? So we have to use this word average carefully. All right, so the median would be perfectly well-defined number, and some people would say that average is kind of an ambiguous term. Do you mean the expectation value of x, or do you mean the median, which would be where the cumulative reaches 1/2? So the same amount on the left as there is on the right. So that's a well-defined place. Even for this distribution with a mean that diverges, I can still compute the median, right? You guys, let me put these ideas into pictures. Okay, so here's my distribution with this case. So that's supposed to be a very long tail, just keeps on going, never really vanishing. And this is the whole area under here. So this thing would be my a minus 1 x to the minus 1.5. And because a was 1.5, we know that a minus 1 is going to be 1/2. All right, so that, what we have learned so far today, is a proper probability distribution, okay? And the problem is that the mean of this distribution is going out here to infinity, okay? I never reach it, okay? And yet the place that I would define as the median might be right here, okay? So that is 1/2 of the total area under the curve, and that means that this point right here would be the median. So the median is a perfectly well-defined thing, and you might look at your children and say they're above average here, but they're not above average according to a definition that uses the mean as average. All right, so we have to be careful with this word average sometimes and clarify exactly what we mean. Okay, let's go on and do part C. given an expression for the fraction of people who make less money than the mean. Okay, so this is a calculation somewhat like the one that I just sketched, except we have to assume that the mean exists in order to do it. Okay, all right. So we have the probability that x is less than mu is an integral from 1 up to mu of a minus 1 x to the minus a dx. So we can go ahead and we can compute this integral now. This is a similar one to the one that we did in part A, right? We're just calculating. In part A, we integrated over the whole domain. In part C, now we're going to stop when we get to mu. And so we get a minus 1 over 1 minus a. I am using the value of the mean here when I put in my integration bounds. Okay, so my mean was a minus 1 over a minus 2, and I'm starting from 1. Okay, so there's a lot of working parts there, but basically all we did was fill in this mean. By the way, this was the answer to part B on the Prairie Learn. Okay, I make sure that I remember to tell you guys what to do to get your points. Okay, so this expression can now be simplified. It comes down to 1 minus a minus 1 over a minus 2, and this is raised to the power minus a minus 1. Okay, so again, we have some issues here. If we have a smaller than 2, less than or equal to 2, we have a problem, right? So this is going to be a quantity that's going to diverge in those cases. Okay, so we can only evaluate if a is greater than 2, because otherwise our mean doesn't exist. Okay, let's go ahead and continue on and do the last part. So for what limiting value of parameter a does the statement everyone is below average become true? All right, so you guys, we already talked about this, right? So we talked about the fact that if I let a be 2 or smaller, then the mean diverges, and that means that everyone is less than the mean, right? So this is I find this to be really really a strange statement, and even more strange that it can actually be true. All right, so you guys know that the answer to that one was a equals 2, and for anything smaller than 2, you'll end up with everyone is below average becoming a true statement, if average means mean. Okay, if we define average to mean the median, then it's no longer true. All right, that's it on that one. Let me give you guys a minute or two to enter your Prairie Learn. We'll reconvene at 11:40 and do the next worksheet. So please, before you come back, before we reconvene, have this next worksheet open, which is about a Schulz-flory distribution. And this one is an example of a case where you normalize the distribution based on, you get the shape of the distribution from physical consideration and have to normalize it. All right, so this is relevant to polymers work. All right, see you guys in 5 minutes. Okay. I think that it's 11:40, so let's go ahead and reconvene now and start. So this next worksheet is about the schulz-flory distribution. This is a member of the gamma distribution family for specific parameters. The gamma distribution has some coefficients that you would find here, and so this schulz-flory distribution is sort of the case where that coefficient would be 1. If you want to, I think it's always helpful to get a quick picture of what we're looking at here. So this is the distribution along K. These represent polymer molecular weights, and so this distribution looks about like this, right? It's got a long exponential tail, or like a geometrically decaying tail specifically. So 1 minus A is the base, not E. But it still looks like an exponential because it's decaying in that exponential fashion. And then at the beginning, it rises in proportion to K. So that's leading term K is the dominant feature here. And the 1 minus alpha to the K minus 1 is the dominant feature over here. And of course, there's a turnover in the middle. So this is our little picture of the molecular weight distribution. This, by the way, is a molecular weight distribution that has been weighted according to the weights of the polymers, which is why it rises with K at the beginning. Normally, it would just be an exponential, right? So there's a very, very fancy way of accounting for the fact that if you do a lot of experiments, what you see is a signal from each polymer that is proportional to the length of that polymer. And so this is a way of working with those cases. And that's why that little K appears in the leading factor. Otherwise, most polymerization mechanisms will just give you a geometric or exponential distribution. All right, enough of me talking about the connection to polymerization, but I do hope you guys appreciate that these things are connected to topics in chemistry and chemical engineering. All right, so this is, I mentioned it's part of the gamma distribution family. There's a little mathematical hint for working with this distribution here. The family of gamma distributions has their name from the fact that all of the operations that you do and integrals that are involved closely resemble the gamma function, which was this integral from 0 to infinity of, by the way, this distribution starts at 0. And you're integrating x to the n, alpha to the x, dx, and the result that you get is n factorial over log of 1 over alpha times to the power n plus 1. Okay, so in this distribution, of course, x, the value of k plays the role of x in the hint, and the value of n is going to be what? It might be a trick question. What will I put in for n?
Does that normalize the function?
Yes. Okay, good. So I think you hit on the essence of the trick question. If I want to normalize the function, I integrate the probability distribution itself. And then the appropriate value of n to use in the hint would be 1. Okay. If I want to compute the mean, I'm going to multiply by an extra factor of x or k. And now the appropriate value of n will be 2. And if I want to compute the variance, I'm going to have to do a calculation to get the expectation value of x squared. And then I would use an n equals 3. Okay, so that's basically how you're using the hint. It's a one hint for all parts of the question. All right, so let's go ahead and do the part of this question that says, find the normalization constant n of a. Okay, this is very similar beginning to the way we started last time. Okay, so we know the shape of this distribution. We don't know what normalization constant goes here. So I know, though, that I want this to be true after I'm done. I want the whole thing to integrate to 1. So this is the calculation that I need to do. And if I go through and do that, I can look at the function that I'm integrating. My integrand has a part that doesn't depend on k. And then the rest of it is, so there are 2 parts that don't depend on k here. There's also a 1 minus a to the minus 1. And everything else I have to keep under the integral sign. So that's going to be k times 1 minus a to the power k dx. Okay, so now I appeal to the hint, and I recognize that this is an integral of exactly the same form as as given in the hint. And I just have to recognize that my alpha here is 1 minus a. Okay, so that alpha corresponds to 1 minus a in the hint. And then I go ahead and plug in the hint. I get n of a times 1 minus a to the minus 1 times 1 factorial because the n corresponds to the 1 here. So I get 1 factorial over the log of 1 over 1 minus a. And remember that the n was 1, so I'm going to square this thing in the denominator, and that's now the result. Okay, so this thing is done, basically. I just have to solve for n, and if I do that, I get n of a is equal to 1 minus a times the logarithm of 1 over 1 minus a, and I have to square that. Okay, so that's the normalization constant. Okay, as long as I use this n of a is equal to this expression back in my distribution, then the whole thing is normalized, and I can talk about probabilities that chains will lie between certain ranges in molecular weight. All right, so
That's none of the possible answers.
oh, it's none of the possible answers. Well, maybe there's some algebra that you need to do to make it look like the one that I have, the one that is offered there. I will let Zichu give you a hint on this because she may have rewritten some of what I did.
I just simplified the log because it's 1 over, so I simplified it.
Oh, yes, very, very good. I didn't notice that you can do that, but there's a very convenient simplification there that Zichu saw. And you know, you guys have to, now and then you have to remember these rules.
Would it have to be a minus 1 then and not 1 minus a?
So the rule has to do with the log of 1 over x is minus the log of x.
Yeah, so then wouldn't you have to change the sign? None of the answers that I can see have a changed sign.
I think because the term's squared, you get rid of the negative anyways.
Good. You guys are
Okay.
working this out together. Okay. That's awesome. Okay. So you can simplify this to 1 minus a log squared of 1 minus a like this. And the reason that you can do that is because I'm going to change the sign of the log when I write it as log of, when I go from log of 1 over 1 minus a to log of 1 minus a, I introduced a negative sign, but it's squared anyway. Okay, so the negative sign just becomes a positive again. Great, so the answer simplifies a bit more than I recognized. Thank you, Zichu. Okay, so now what we want to do is to compute the mean molecular weight, and so that is going to require doing this calculation, and that calculation looks like this. We've got an integral from 0 to infinity, k rho of k dk. Remember that that's going to be now I have 1 minus a log squared 1 minus a out front. I have a 1 minus a to the power minus 1 that's going to come out of the distribution. And so that's going to get rid of this thing. Okay. And what else can I do here? I don't think I can do anything else. All right. So my integral now has a k from here, and there's also a k in here. So now I end up with a k squared, and I had a 1 minus a to the power k, and I'm integrating that over k, and I'm going from 0 to infinity. Okay, so I can now use the hint again. Okay, so let's go back up here. Use the hint. Okay, so now I'm going to let n be 2, And again, alpha is 1 minus a. And so let's see if I can do this. All right. So the answer that I got in my notes is maybe a little bit different from what Zichu has in the Prairie Learn, and I'm trying my best to stay with the new version of that thing. But that means I have to do it in real time, which means you guys get to see that I make algebra mistakes too. All right. So let's see if we can finish this thing off. So we have this is going to be 2 factorial over the log of 1 over 1 minus a to the power 3. Okay, so that is log squared of 1 minus a times 2 over the log of 1 over 1 minus a, and we're raising that to the 3rd power now. So this is a interesting little thing because I know that 2 of those powers are going to cancel with the one that we already did for the same reasons, right? So this is going to be just 2 over the log of 1 over 1 minus a. Zichu, tell me if I'm getting this right. So that's going to be 2 divided by negative 2 over the log of 1 minus a. This might look like we have a problem here, but remember that a is typically a small number, which means that 1 minus a, small positive number, which means that 1 minus a is going to be a number less than 1. And the logarithm of a number less than 1, what sign does it have?
Negative.
It's negative. Okay, so that's good. It wouldn't make any sense for my polymers to have an average molecular weight that was less than 0. So we've got something less than 0 here, and we're multiplying it by something negative. And so this whole thing ends up being positive. Zichu, did you make this simplification, I think, again?
Yes, I did this for all the parts.
Okay, great. So so this ends up being that is the final answer then, I guess. That can't be made any more simple than this, right? Tell me if I left out a step, Zichu.
Yeah, this is the final answer.
Okay, great. And everybody sees that that is a positive number, right? So always good to go back and do a little sanity check, ask whether your answers make sense. We know that we started out with a distribution that had support only for numbers greater than 0. There's no possible way I can get a mean that's less than 0. And indeed, this is a number that has to be positive. All right. So let's do now. This is becoming practice with integration here. All right, so let's do this case where we compute this quantity. All right, so this is not the variance, right? The variance would be this one. Okay, but this is related to the variance because we know we can always do this. We could take e to the k squared minus e to the k. Sorry, expectation value of k squared minus the expectation value of k quantity squared, and that should be the same as the variance, right? So this is sigma squared, and that's the sort of conceptual definition on top, and we often refer to this as the computational definition down below, right? So it's not really the definition at all. It's just a convenient recipe. All right, so you can see how it's a convenient recipe in this particular distribution because we have a hint to work out integrals like the one that's going to arise when we do the expectation value of k squared. This one doesn't fit the pattern. We would have to do some expansion, but we've already computed this. If we can just compute this piece, then we will have the information needed to do that. All right. So let's do this calculation. I'm going to, in the interest of time, it's 11:55. I'm going to post this on the web and trust that you guys can see how this is working. We're going to get some simplifications here that will do things like this. Now we have a k to the third, 1 minus a to the power k dk dot dot dot. Lots of steps that are really just integration again, using that hint. And the answer that I get at the end is that E of k squared is 6 divided by, in my notes, it was 6 divided by 1 over 1 minus alpha to the power 2, okay, which Zichu wisely would have taken and said that that's negative. In the basement, that's a negative log of 1 minus alpha. And then I'm going to square it, so the negative doesn't matter. And I have log of 1 minus alpha like this. Okay, so that is now the expectation value of k squared. And there's I think, quite a nice little note here in the exercise that that it's a very common measure of the width of the distribution of polymers to report something called a polydispersity. Okay, that's a little D bar basically. So you have H bar and now you have D bar, and D bar is the expectation value of k squared divided by the expectation value of k quantity squared. Okay, why that represents width? That's kind of a lecture for another day. Personally, I wish they would just go ahead and do this calculation and report sigma over the mean. But that's not what they do. In the experimental literature, they report something else. And so an extremely narrow distribution has a polydispersity of 1. And a distribution that's very wide has a polydispersity that goes to a number much larger than 1, often like 10, 20. And so, so this is not the same as reporting this. So I could imagine doing this, which is the way a statistician would report this. And let me just say a little bit about this. Okay, so so in the experimental literature, you will see polydispersity, and once in a blue moon, usually a theorist will do the following. Okay, so if we have a narrow, let me call this monodisperse. Okay, so that would mean that my distribution is very sharply peaked. All the polymers have exactly the same molecular weight. This dispersity, or polydispersity sometimes is called, is 1. Okay, and this thing goes to 0. And for a broad distribution, that would look something like the schulz-flory, for example. The schulz-flory happens to have a dispersity of 2. Okay, so if you go through and you compute this thing, it ends up giving you 2. But so this is, but for a broad distribution, the schulz-flory is not considered a broad distribution. That would be one more like a log normal or a power law distribution, would have a number much, much greater than 1. And this also becomes much, much greater than 1. Okay, so you can compute one from the other. But anyway, this is the experimental way of doing this, and this would be the statistics way of doing this. And how I wish I could take this field and convert them to doing that, but it's too late. All right, so this is the convention. They report the second moment over the first. All right, let's go ahead and do the last exercise here with the last few minutes of the class. So there's one more worksheet, and this one has to do with ideal gases. So if everybody can go ahead and open that one up. So this is worksheet 3 for today. And our first problem in this worksheet asks about the number density of an ideal atomic gas. Okay, so we have a gas at, when we talk about number density, we really just mean concentration. The only difference is that we don't count by moles, we count by individual molecules. Okay, so we have a gas at concentration C, and and that represents atoms per unit volume. Okay. What is the probability that 2 units of volume contain no gas molecules? All right, so what are we going to do here? So we're going to let X be equal to the number of molecules in our observation volume. And we want the probability that X is equal to 0. And what's it going to be? Let's let V be our unit of volume. All right. All right. So if we have 2 units of volume, then I'm starting to write the answer here. What is it going to be? So what distribution are we going to use? Hey, did you guys log off?
Poisson distribution.
Poisson distribution, yes. Okay, so this is the Poisson with the case 0. So the Poisson, remember, is going to be lambda to the x and x to the minus lambda, and then we're going to divide by x factorial. So in this case, x is just 0. So all we have is lambda to the e to the minus lambda term is all that we have. So this is going to be e to the minus 2, let me write it as c times v. Okay, so if I have 2 units of volume, I have 2v multiplied by the concentration. That is the expected, this, if you want, is my lambda parameter. All right, and we're just using the Poisson distribution here. Okay, so that's really the entire answer to that problem, minus 2 CV. Okay, so now the second part of this question, for the gas in the first part of this problem, what is the probability density that you will find a neighbor at a distance r to its nearest neighbor, right? So let me say that more clearly. I think I bungled the explanation. All right, so we want rho r of r, where r is now defined as the distance from a given particle to its nearest neighbor. And let's think for just a moment about what this distribution should look like. Okay, so if we consider a distance that's very small, it's really unlikely that in the little tiny volume corresponding to the distance, a very small distance from our tagged particle, that we will find another one. Okay, and so we expect the distribution to go to 0 at very small distances. As we let the distance become larger, it becomes more and more likely that we'll encounter our first particle because the volume is getting bigger with r. But eventually we get to large r, the probability that we'll encounter our first neighbor at a very large distance is going to go down again, right? Because we'll surely have encountered one a lot closer than that. Okay, you guys see all the considerations that are in this question. Now, really, we know that the probability density to identify a particle in this volume V is C e to the minus CV. Okay, if we were talking about a Poisson process before, with concentration C and observation volumes given by V or some multiples of V, then now we're talking about finding that how long in volume you have to wait to get to your first neighbor is going to be an exponential process. Okay, they are always duals of each other, right? They always, once you know one of them and the parameters that go into one, you can always convert the problem into how long I have to wait to see one. Okay, so we had Poisson, and here we have exponential. Okay, so these are corresponding things. We talk about the probability that there will be none in a volume V. So let me, now you've already answered part A, so I'm going to erase this 2 units. Okay, so we have 1 unit of volume V. So if the Poisson is e to the minus CV, the corresponding exponential is C e to the minus CV. And we just interpret them differently. One of them is how far in volume you will have to go in order to see the first one. And the other one is what is the probability that you will see 0 in that volume. Okay, so these 2 things can be interconverted. So now what do we do when we have a probability distribution as a function of one variable and we want to change it to another one? Okay, so I'm going to imagine that my volumes are little spheres around here's my tagged particle, and I go out to some volume around him. So this volume is now V equals 4/3 pi r cubed. Okay, so V is a random variable and R is a random variable, but there's a clear mapping between the 2 of them. Okay, and it's a monotonic mapping between the 2 of them, which makes this particularly easy to do. Occasionally we encounter situations where the mapping is something that goes up and down, and then it becomes a harder calculation. We're not going to do that just yet. I'll teach you some tricks to do that next week. Well, maybe the week after this. All right. So this is the distribution of volumes. So we're basically looking at our field of other particles here, and we're saying, what's the probability that I haven't encountered one yet as I expand this volume? Okay, and I can expand that volume and I can keep track of it in terms of its volume, or I can keep track of it in terms of R. And I should be able to write down the probability distribution either way, because they really mean the exact same thing. And if they mean the exact same thing, then basically what we can do is say that if rho of V dV represents the probability that I find the first particle in this little slice of thickness dV around my initial volume, then rho of R, I changed my, here, I can do this. Then I should be able to write down that these 2 things correspond to exactly the same measure of probability, right? So I can think about a sphere slightly bigger, and has so this sphere, the dashed line has volume V plus dV, and it also has a radius R. And if I go out to the dashed line, I have R plus dr. Okay, and the amount that the probability distribution changes, that is the probabilities within the two little concentric spheres, they should be the same. Okay, so now we have a recipe for converting a distribution from one variable to another. Okay, so rho of R, if I wanted to solve for this, what I would do is just, what I want to do is solve for this thing, and I get that it must be rho of V dV. Oh, sorry, I messed that up. Rho of V multiplied by dV dr. Now I want to be careful here, because in principle, I need an absolute value sign over this. Okay, I could, the formula in this case, it doesn't matter because V is an increasing function of R. But in practice, I can do the exact same considerations if V is a decreasing function of R. What matters is the thickness of the 2 shells, right? How much V changes and how much R changes, they correspond to each other, and the sign doesn't matter. You take in the same amount of the total axis in the 2 cases, okay? So all that really matters here is the absolute value. The sign is irrelevant, and we always keep the positive one. Okay, so let's go ahead and write this down. So this was C. So this part becomes CE to the minus CV. And the dVdr, what is that going to be? That's going to be, dVdr is going to be 4 pi r squared. All right, well, it's not really a distribution as a function of r yet because I still have v's floating around in my formula, but that's a sort of trivial step here, is to replace the v by the 4/3 pi r cubed times c. Now I have my 4 pi r squared, and that now is the probability density as a function of the new variable r. Okay, so what does the density as a function of r look like, and what does the density as a function of v look like? So when we plotted it in terms of v, I had an exponential decay. So this was c, this was c e to the minus cv. Okay, so that's the probability density to find the first particle within a volume v around my tagged particle at the origin. Okay. After I convert it, I get something that looks like this. Notice it starts out with a 4 pi r squared times c coefficient in front, and it ends up with a e to the minus r cubed. That's a really fast decaying exponential. So it's going to do something like this. Okay. And why is it doing that? It's doing that because, you know, all of these little, so let's suppose that we pick out a radius here. That little sliver to the left in this distribution mapped onto the little tiny sliver that barely moved here. When I take a small sphere in volume, it has an even smaller radius, right? So I had to go out to a very big radius comparatively to get any noticeable change in the probability distribution. And that's why this, when I map this thing to R, it starts out very small and flat. Now, on the other side of the distribution, we have the opposite thing happening. Now the volume is decaying, the volume is growing, and it doesn't take very much change in R because it's cubed to make a huge change in V. And so the tail of this distribution drops off much faster than the tail of the distribution in V. Okay, so and yet these two distributions are completely equivalent representations of the same idea. Okay, hopefully that is helpful. I think I answered the question on the Prairie Learn site. You can type in your answer there, but you know, of course, the important thing is to recognize that when we have a random variable that is related through some monotonic relationship to another random variable, we can always change our two distributions to think of one versus the other. Very useful thing. So if you do an experiment and you keep track, for example, of the size of your nanoparticles that you make, and then somebody, and you say, you know, I have a collaborator who does this all the time. Well, my size distribution is this. And I say, did you compute that using the volume of the nanoparticles, or did you use their radius? And he looks at me and says, what do you mean? Okay, well, they're different distributions. Like if all you have is the curve and you're told it's a size distribution, you really don't have enough information to do this. It's exactly this situation, right? So you've got a mapping between the two quantities that is it's one-to-one, but it's not a line. And so the distributions are going to be transformed versions of each other, and they won't look exactly the same. All right, so hopefully that gives you guys some help as to ideas as to where you would use these things. Any questions? I've filled the whole hour and 15 minutes here. Okay. So we have a quiz again next week. We'll do more worksheets on Tuesday, and maybe cover some aspects of the Gaussian distribution on Tuesday. And And then, so we haven't really used the Gaussian distribution very much, but for the remainder of the class, it will be the star character. It's all the things that we're going to do from here on out are going to be closely related to Gaussian statistics. All right, I think that's it. Have a good weekend.